Welcome to another video. In the last video, we've discussed some multiple choice questions from thermodynamics. In this video, we are going to discuss question answers from thermodynamics, majorly from Carnot engine, Carnot cycle, and the efficiency of engines. Let's get started. The question here says, why is it not possible to construct a heat engine that will not expel heat into the atmosphere? In other words, that will convert 100% of the input heat to the useful work. In other words, an engine that is 100% efficient. Let's just see. Percent efficiency for an engine is represented with this formula, where this T2 is the temperature of cold reservoir or the temperature of sink, and this T1 is the temperature of hot reservoir, in other words, temperature of source. What it takes for this ratio to give you 0, because this is the only way we'll get 100% efficiency. If this ratio becomes 0, we'll get 1 minus 0 multiplied by 100, which is 100%, right? So in order for this ratio to turn 0, it is only possible if this T2 becomes 0. What is this T2? This T2 is the temperature of sink. And keep this thing in mind, we have already discussed that in this equation, this T is not the temperature in Celsius. This T has to be in Kelvins, right? Now, let's just look at it once again. Is it even possible to reach 0 Kelvin? No, it is not. 0 Kelvin so far is an unattainable temperature. This is the reason it is not possible to construct a heat engine that will not expel the heat into the atmosphere, right? Then draw a schematic diagram of a heat engine. What a heat engine exactly is? A heat engine is a device which converts heat energy into mechanical work. We have source or hot reservoir here at temperature T1, and then we have a sink or a cold reservoir here at a comparatively lower temperature. Let's call it T2. And then we have a working substance, maybe an ideal gas, which expands when Q1 amount of heat is received by the substance. As a result, this working substance converts fraction of the input heat Q1 into some useful work W, and then rejects the remaining amount of heat, call it Q2, to the cold reservoir, that is to the sink. For the work to be done by the system on the surrounding, it is important that the source temperature be greater than the sink temperature. The greater the difference between cold and hot reservoir's temperature, the greater will be the efficiency of engine. So if we want the engine to be 100% efficient, it is only possible if T2 is equals to 0. And if we want to see at what temperature the efficiency of engine will be 0, just put these two values equal, right? So as soon as the temperature of source and sink becomes equal, this ratio gives 1, 1 minus 1 gives 0, 0 multiplied by anything gives 0. That is, whenever the source and the sink are at same temperature, no matter how high the temperature be, efficiency of engine will become 0. That is, no heat will be converted to the useful work. Then it says name the device shown in the given diagram and define it. Heat input is given to the water. This heat then gets converted into steam. This expanding steam then pushes the piston, which as the result keeps this wheel moving. See, work is being done by the system on the surrounding. Do you see any resemblance in these two systems? Heat input, work done by the system on the surrounding, right? So this is nothing but a heat engine. And how do we define heat engine? Heat engine is a device that consists of two bodies at different temperatures and a working substance. Heat is absorbed by the working substance, and the working substance converts fraction of this input heat into useful work and then rejects the rest of it to the cold reservoir. In other words, heat engine is a device that converts heat energy into the mechanical work. Then label the given diagram, identifying the necessary components of the above device. What is it? Again, it is a heat engine. See, we have a body at temperature T1. Let's call it hot reservoir, right? Heat is absorbed from this hot reservoir by the working substance, and this working substance performs some work on the surrounding and then ejects fraction of the input heat to the another body at comparatively low temperature T2. This body is what we call cold reservoir, or we can also label it as sink and source. A schematic diagram of a Carnot engine. Carnot engine is an ideal heat engine, right? Carnot engine using an ideal gas as the working substance is shown in this diagram. We have ideal gas here as the working substance. We have thermal reservoirs, source at high temperature and then sink at low temperature. Show that the efficiency of Carnot engine is 1 minus T2 over T1. How do we write efficiency? We say efficiency is the useful output energy over the input energy, right? In case of heat engine, this Q1 is the input heat. So we'll replace input with this Q1, right? What is the output of the engine? The engine is performing some work on the surrounding. This work here is the output, right? Then we know that this work equals the difference between the input heat and the heat rejected to the cold reservoir. In other words, we can rewrite this W as Q1 minus Q2 with this Q1 in the denominator as it is. Let's just simplify this. Let's just first LCM break. Let's just cancel them out. It becomes 1 minus Q2 over Q1. We know that in thermodynamics, heat can be related to the temperature in Kelvin. So we can rewrite this equation as efficiency equals 1 minus T2 divided by T1. This is nothing but the equation for the Carnot engine that you were supposed to derive, where this T2 is the temperature of cold reservoir or the sink, this T1 is the temperature of hot reservoir or the source of heat, and this eta is the symbol used to represent the efficiency of engine. If a Carnot engine performs 500 joules of work done by the system is 500 joules, and at the same time rejects 2000 joules of heat energy to its cold reservoir. Heat rejected to the cold reservoir is represented with Q2. It is 2000 joules. Remember, heat supplied by the source will be represented with Q1, and that rejected to the cold reservoir will be represented with Q2. Find the percent efficiency of the Carnot engine. Percent efficiency is what we need to calculate. We can write percent efficiency as useful work over the heat input times 100, or we can also write it as 1 minus Q2 over Q1 multiplied by 100. It is up to you. Either way, you will end up getting the same answer. See, we already know the work done by the system. All we need to do is first calculate the heat supplied by the heat source and then just put in this equation and you will get to know the percent efficiency. We know that the heat supplied performs two tasks. First of all, work is done by the system and then the remaining is rejected to the cold reservoir. So we can write Q1 equals W plus Q2. Just put in W and Q2. Work done was 500 joules and the heat rejected was 2000 joules. That is, heat supplied by the source is 2500 joules, right? Just put these values in this equation. I would like to go with this one. You can go with whatever you feel like. Percent efficiency is work done by the system 500 joules, heat supplied by the hot reservoir 2500 joules multiplied with 100 ones, fives. 100 over 5 is nothing but 20%. That is 20% of the input energy is converted to useful work, whereas the 80% of the input energy is rejected to the cold reservoir. Then a Carnot heat engine with an efficiency of 65%, percent efficiency is 65%, absorbs heat from a reservoir at 590 Kelvin. See, heat is absorbed from the source, that is from the hot reservoir. इसका मतलब है फिर this must be the temperature of hot reservoir, and we used to represent the temperature of hot reservoir with T1. So T1 is nothing but 590 Kelvin. Calculate the exhaust temperature of the engine. We know that heat is ejected or the heat is dumped to the cold reservoir, which we also call sink, or the exhaust. So the temperature of exhaust, that is sink temperature or the cold reservoir's temperature, T2, needs to be calculated. First of all, write down this efficiency in terms of temperature. We'll write 1 minus T2 over T1 into 100. If percent efficiency is 65, just put it in here, and the temperature of the hot reservoir is 590 multiplied by 100. This 100 goes into the denominator here, and the 65 becomes 0.65, which is 1 minus T2 over 590. Let's just shift this T2 over 590 here. It becomes T2 over 590 equals 1 minus 0.65, which is nothing but 0.35. And since we are to calculate T2, let's just make this T2 the subject of our equation and shift this 590 to the right side of the equation. This becomes 0.35 multiplied by 590. Before calculating, we already have an idea that since this T2 is the temperature of sink, right? Sink has to be on lower temperature compared to that of the source. So it is obvious that the final answer should be less than 590 Kelvin. And this equation suggests the same, because whenever we multiply a number with a number which is smaller than 1, we always end up getting a smaller number, right? 0.35 multiplied by 590 is nothing but 206.5 Kelvin. So the temperature of sink is 206.5 Kelvin. उस case में the efficiency of engine would be 65%. Let's just see what else do we have. They are saying that the difference in the temperature of water at surface of the ocean and the bottom of the ocean for operating a heat engine was discussed. If they observed 20 degrees Celsius as high temperature, that is the temperature of source, 20 degrees Celsius, the temperature of heat source, and 4 degrees centigrade as low temperature, that is temperature of sink or the exhaust or the cold reservoir. T2 is 4 degrees centigrade. Then calculate the efficiency of engine. You need to calculate the efficiency. So first of all, recall the formula for efficiency in terms of temperature. We know that efficiency is 1 minus temperature of the sink over temperature of source. Right? It has already been established that we must put in the values of temperature here in Kelvin and not in degrees centigrade, right? So first convert these centigrades to Kelvin by adding 273. So the temperature of source becomes 293. it becomes 293 Kelvin, whereas the temperature of sink becomes 277 Kelvin. Just put in these values here. 1 minus 277 over 293. Divide these values, 1 minus answer, and then you will get to know the efficiency. 277 over 293 is nothing but 0.945, and 1 minus this answer gives you 0.054. That is, the engine is 5.4% efficient. And it makes sense because we've discussed that the greater the difference between the sink and source temperature, the greater will be the efficiency of engine. Because the difference here is almost 16 degrees, right? So it makes sense that the engine is not very much efficient. Next, given picture shows a schematic diagram of a refrigerator. Describe how a refrigerator works on the reverse principle from that of a heat engine. This is a refrigerator. Refrigerator is the reverse of heat engine because in case of heat engine, heat flows from hot reservoir to the cold reservoir. Whereas in the case of refrigerator, heat flows from cold reservoir to hot reservoir. In case of heat engine, work is done by the system on the surrounding and therefore this arrow points outwards. Whereas in case of refrigerator, work needs to be done by the surrounding on the system in order to force this heat to flow from the body at low temperature to the body at high temperature. आपके पास पेपर का एक क्वेश्चन है which says अगर एक रूम में रेफ्रिजरेटर के डोर को ओपन कर दिया जाए तो क्या ख्याल है, क्या उस रूम का टेम्परेचर मजीद लो हो जाएगा, सेम रहेगा या बढ़ जाएगा? सी, हीट इज रिमूव्ड फ्रॉम द सब्सटेंस जो भी रेफ्रिजरेटर के अंदर है, राइट? लेकिन दिस सेम अमाउंट ऑफ हीट इज नॉट इजेक्टेड टू द सराउंडिंग. उस हीट के अलावा एडिशनल work is also being done and this energy is also being ejected to the surrounding, that is to the room. इसीलिए exhaust में जो heat dump की जा रही है, it is very large than that extracted from the cold reservoir. This is the reason that temperature would never drop, it would rather increase because ज्यादा amount जो है वो dump किया जा रहा है surrounding में. And let's just see one last question from Carnot cycle. A Carnot engine using an ideal gas as the working substance is shown in the given PV diagram, that is pressure volume plot, right? It consists of 4 processes labeled as 1, 2, 3 and 4. Label the given PV diagram with the name and the directions of these processes and also describe each of the 4 processes. We've discussed in lecture 10A from Thermodynamics MCQ questions that this is a cyclic process. Your system started from point 1 and all the way it ended to point 1 as well. Let's just discuss it stage wise. Pehle to we need to just label the processes. We already know that this is isothermal expansion क्योंकि 1 से 2 तक जाते हुए वॉल्यूम इंक्रीज हो रहा है, राइट? 1 पर वॉल्यूम कम था, 2 पर वॉल्यूम ज्यादा है. And then there's a stage 2 is adiabatic expansion. Again, volume increase हो रहा है, but this time the change is rapid, right? और आपके system के temperature में भी change आ रहा है. And then this third stage is isothermal. Gradual है, temperature same रहेगा, but in this case it is compression because अब system का volume कम हो रहा है. Start में जो भी volume था 4 पर पहुंचते हुए volume अब decrease हो गया. And then this is again compression because 4 से 1 तक जाते हुए volume फिर decrease हो रहा है. But then this is adiabatic compression, not an isothermal compression because this is rapid. ठीक? आप इसे explain कैसे करेंगे? 4 processes को आप कैसे explain करेंगे? आप कहेंगे from going from 1 to 2, temperature of the system is T1, volume has increased and pressure has decreased. Second stage में system is going through the adiabatic expansion. That is, no external heat energy is being supplied to the system. System is expanding on the expense of the internal energy. Internal energy of the system is decreasing और उसके रिजल्ट में आपका सिस्टम जो है कुछ ना कुछ वर्क कर रहा है. एंड जब मैं कहती हूँ मेरे सिस्टम की इंटरनल एनर्जी डिक्रीज हो गई, तो इसका मतलब है मेरे सिस्टम का टेम्परेचर भी ड्रॉप हो गया, बिकॉज आइडियल गैस में इंटरनल एनर्जी इज डायरेक्टली रिलेटेड टू द टेम्परेचर ऑफ सिस्टम, राइट। तो अगर मैं कहती हूँ यहाँ पर टेम्परेचर वाज T1, तो अब टेम्परेचर हैज ड्रॉप्ड टू comparatively smaller value, that is T2. फिर थ्रू आउट दिस स्टेज 3 विच इज आइसोथर्मल कंप्रेशन, सिस्टम का वॉल्यूम कम हो रहा है, प्रेशर इंक्रीज कर रहा है 3 से 4 पर आते हुए, बट टेम्परेचर रिमेन्स कांस्टेंट। और जब मैं कहती हूँ टेम्परेचर कांस्टेंट है, तो इसका मतलब है सिस्टम की इंटरनल एनर्जी भी कांस्टेंट। देन इन दिस लास्ट एंड द फोर्थ स्टेज वॉल्यूम डिक्रीज हुआ है, right, in going from this point 4 to point 1. So we'd say that this is compression और ये adiabatic compression है। इसका मतलब है again system was perfectly insulated, कोई heat transfer नहीं हुआ system और surrounding के दरमियान, और फिर यकीनन system ने इंटरनल एनर्जी का चेंज एक्सपीरियंस किया, राइट। हमें पता है जब भी सिस्टम्स एक्सपैंड होते हैं उनका टेम्परेचर डिक्रीज कर जाता है, इसलिए हम कहते हैं उनकी इंटरनल एनर्जी कम हो गई। और जब भी हमारे सिस्टम्स कंप्रेस होते हैं, हम कहते हैं मॉलिक्यूल्स हैव मूव्ड क्लोजर टू ईच अदर, उनका कोलिजन जो है वो बहुत फ्रीक्वेंट हो रहा है, किनेटिक एनर्जी, एंड देयरफॉर द टेम्परेचर ऑफ द सिस्टम हैज इंक्रीज्ड। इसका मतलब है इस फोर्थ केस में मैं कहूंगी मेरे सिस्टम की इंटरनल एनर्जी भी इंक्रीज हो गई, राइट। सो ऑल इन ऑल 1 पॉइंट से स्टार्ट करके वापस 1 तक आते हुए सिस्टम ने बीच में 2 स्टेजेस पर चेंज ऑफ इंटरनल एनर्जी एनकाउंटर किया है, बट द ओवरऑल चेंज इन इंटरनल एनर्जी इज 0, right? This is why we say that at the end of this complete cyclic process, the resultant change in the internal energy is 0. And by the way, this area under this PV curve is what we call the work done by the system. This was the last question from Carnot engine. Let's just end it here. In the next lecture, we will solve some questions from first law of thermodynamics and we'll derive some expressions for thermodynamics. Till then, Allah Hafiz.